In the last video, we had developed the relations for a simple harmonic oscillator by studying the system of a mass on a spring. One of the key results we got at the end of that was that at all times the acceleration of an object in simple harmonic motion was minus 2 pi over the period squared times the position. Now it turns out that any system that can be written in this form is a simple harmonic oscillator. So it doesn't have to correspond to purely a mass on a spring. Anything where after suitable massaging of it, we can get it into a form where the acceleration equals negative stuff times the position. That is a simple harmonic oscillator, and the stuff is the square of 2 pi over the period. And this is even more general than it might look. This not only works for linear variables like a and x, but this would also be true if you can write it in angular variables. If you can take a system and get it into a state where the angular acceleration is equal to minus stuff times the angular position, then again, that is a system that will be undergoing simple harmonic motion. And the stuff between the minus sign and the position is 2 pi over the period squared. So it turns out that a lot of systems in nature, especially if you don't displace them off of equilibrium very far, either are or can be very well approximated as simple harmonic oscillators. So I'm going to go through and give a few examples. One example that you tend not to see in very many places, but I think is a very instructive place to start, is a system called the torsion pendulum. You might have actually seen something like this. There are certain decorative display clocks where the pendulum is often like 4 spheres that are connected to a piece of spring steel, and it spins back and forth, and it's that spinning back and forth that drives the clock. I'll make mine a little simpler. So in my version of it, we'll have some sort of a vertical support, and then we'll have a thin piece of spring steel or just a thin wire, anything like that. And then, just for the example here, we'll attach a disc to that piece of spring steel or wire. So the disc will have some moment of inertia I, and it works out that, and let's say here that this is our equilibrium position. So let's say we go ahead and give that twist out to some angle plus theta. And then what will happen is it'll twist back and forth in moving the fastest through the equilibrium angle and turning around at the extrema, the amplitude angles here, plus and minus capital theta. And what's making this twisting back and forth happen is the piece of spring steel. And it'll turn out that the spring steel will exert a torque that is proportional to the angle. Now this letter here is a lowercase Greek kappa. You would draw one like that. That's called the torsion constant. Not that I'm trying to make that big of a deal of it here, because I just want to use this as an example of how we can use the general expression of a simple harmonic oscillator to recognize that this is 1 and to figure out a relation for its period. So we can start with the torque that the piece of spring steel would exert. So we're saying that the torque, it'll try to untwist, and how hard it'll try to untwist is directly proportional to how much it's been twisted. By Newton's second law applied to rotations, the torque would also be equal to I alpha. So alpha would equal minus kappa over I times theta. And you go, hey, wait a minute. This is the form of a simple harmonic oscillator. We've got an acceleration of some sort here. We've got a position of some sort here. We have a minus sign. Those are all important. That means you can just plain stop. You know that this is a simple harmonic oscillator. You know that the angle is going to go as cosine of 2 pi over t times 2 pi over capital T times t. You know all of this automatically. This bit right here you will identify as having to be equal to 2 pi over the period squared. So you can then conclude that this is going to execute simple harmonic motion, and we can find the period by saying that 2 pi over the period is equal to root kappa over I. Now, I started there because I want to work towards the simple pendulum, which is just a mass at the end of a string, a small mass at the end of a string. But as a step along the way, I would like to develop the physical pendulum. So in our physical pendulum, what I imagine is to just have some sort of amorphous blob here. And it's fixed to rotate about this axis right here. Let's say its center of gravity, its center of mass, is located right here. And we'll say that this distance from the axis to the center of gravity is h. So here I've got it tilted off at some angle theta with respect to vertical, which would clearly be the equilibrium position. There are two forces acting on it. There will be a force due to the normal force of the pin in the axle, trying to push it up, and a force of gravity trying to push it down. So the torque that we will exert will be the force of gravity times the lever arm, which is going to be h times the sine of this angle, because this distance right here is our perpendicular. That's equal to h sine theta. So my lever arm is h sine theta. And then here you can see if I've got this pulled over to, in the clockwise direction, the torque would be counterclockwise. And if I've got it counterclockwise, like I've got here, the torque would be clockwise. So we need a minus sign to take that into account. All right. So the force of gravity is mg, so let's just make that substitution. And then we can say the torque is equal to I alpha. And then we get that alpha will be equal to minus mgh over I sine theta. Now this does not fit our functional form. So it is not a simple harmonic oscillator yet. And if you need to do it carefully and you need to use this functional form, there is an answer, and it's a horrifying thing called an incomplete elliptic integral, the first kind. And yes, there is such a thing as an incomplete elliptic integral, the second kind. And yes, there are also complete elliptic integrals, but we really don't need to go there. So we can ask ourselves, so is there a regime where we don't have to resort to such horrifying things that come from the methods of calculus? And the answer is yes. If we keep our angles small, say below about 20 degrees or so, this is a good exercise to do if you got your calculator nearby. Put your calculator into radians and take the sine of 0.1. If you do that, you'll see that you get a number that's just a titch less than 0.1. And then try that again with 0.2. And you'll get a number that's a slightly bigger titch less than 0.2 than you were 0.1. And then the same kind of deal with 0.3, which that's about 20 degrees. If you try to push your luck much further, then it starts the value of sine theta versus theta itself in radians starts to diverge too much. But if the angle is small and we're in radians, so let's also put that in. Oop, come on. So the angle is in radians. We can approximate that sine theta is approximately theta itself. And that will allow us to make more progress on our physical pendulum. We can then say, all right, alpha will be approximately minus mgh over I, just plain times theta. Then you look at that and say, hey, this is an angular acceleration. That's the corresponding angular position. There's a minus sign. This is a simple harmonic oscillator. So as long as angles are small, this thing will oscillate in a simple harmonic oscillator type fashion. And this bit right here would be 2 pi over the period squared. So what we get is that 2 pi over the period for this system is equal to root mgh over I. With that in place, I can now go ahead and look at the simple pendulum. So we'll recycle this result. In fact, I will go ahead and copy it right now. There we go. So the simple pendulum is just a mass at the end of a string. So here I've got a ceiling, I've got a very thin lightweight string attached to it, and then I put a mass out at the end of the string. We'll say this length is L. This would be my angle theta here. And this would be my axis of rotation right here. So if I want to treat this as a physical pendulum, which I certainly can, I just identify that in this case the distance from the center of mass to the axis of rotation is also L. So we can reuse our simple pendulum. Whoops. Doggone it. We could reuse our simple pendulum result if my software wouldn't be glitching on me. Okay, so much for that. Doggone it. Stop it. There we go. We can reuse our simple pendulum result from before. But now we can go ahead and start to put in for H and for I. So we identified that H was equal to L. So what about the moment of inertia? Well, this is just a point mass. And usually you write that the moment of inertia of a point mass is mr squared, where r is the distance from the mass to the axis of rotation. So that means that in this case, L is also equal to R. So instead of writing mr squared here, I'm going to write ml squared. Turns out that all that matters is that you have a mass to your pendulum bob, and that'd be significant enough that air resistance isn't going to be a problem. And then we cancel out. We get that 2 pi over t is equal to root g over L. And here, let's actually go to the effort to get t all by itself. So this is going to involve a little cross multiplying. You'll get that the period is 2 pi root L over G. So the period of a pendulum depends only on, of a simple pendulum, depends only on two things: the length of the string and the gravitational field strength of the planet you're on. So as an example of this, let's say that on Earth here, you built yourself a pendulum, and the length of the pendulum is 2 meters. Now let's say your friend on the moon, let's see how well I can draw a spacesuit. It's probably not going to go very well at all. Well, it has certainly been worse. Your friend on the moon, so let's say L Earth here, wants to construct a pendulum, a matching pendulum that would oscillate with the same period. Now the thing is the gravitational field strength on the moon is approximately 1/6 that of the Earth. So how long should your friend make the pendulum string? Well, we can, since we want the period to be the same, we can demand that t on the moon equal t on the Earth. So we'll demand that 2 pi root L moon over G moon equal 2 pi root L Earth over G Earth. Okay, and then our first small favor is that the 2 pi's cancel, and then we can square both sides and be left with L moon over G moon is equal to L Earth over G Earth. So the length on the moon will be the ratio of G moon to G Earth times the length of the pendulum on the Earth. But we said that the gravitational field strength on the moon is 1/6 that on the Earth. So now that cancels, so we get that the length on the moon would have to be 1/6 how long it was on the Earth. Since you made it 2 meters long on Earth, it needs to be 1/3 of a meter long on the Moon to swing at the same rate. So you can see that gravity pulls a lot weaker on the Moon, and things tend to swing around weaker. This is part of the reason why in later Apollo missions the astronauts had those special lunar rovers. I've seen some social commentators say, "Oh, isn't that classic 1970s America? Driving your car around on the Moon." Well, I won't necessarily go there because I'm not a sociologist. But what I can say is if you ever watch a video of astronauts walking on the Moon, you find that they can't. They pretty much had to resort to doing a bunny hop kind of a move. And that is because if they tried to walk, walking is a bit of a controlled fall, and since everything was happening so much slower, the body, sort of the pendulum motion of the body as it walks was happening way too slow for what the lengths of all the joints had evolved to expect. As a result, astronauts attempting to walk on the Moon pretty much all universally ended up falling over. Now you say, well, what's the big deal about that? Well, what happens if you crack the shield of the face mask on your spacesuit, or damage your oxygen equipment or something like that? That could end really, really, really badly. So the lunar rover was developed in order to keep astronauts from falling by keeping them from needing to walk in the first place. So in the next video, we will start taking this and simple harmonic motion, and we'll go in a bit of a different direction as we start looking at the propagation of waves. Catch you in the next one.